Greetings and welcome to Calculus in the PM. I'm your host, Mr. Sundell. Hello. Hey, Papa Joe. Okay, anyways, 2.2. Limits involving infinity. And you know the infinity symbol, right? Okay. A few things here. First of all, the symbol for infinity does not represent an actual number. We use that symbol, infinity, to describe the behavior of a function when the values in its domain or range outgrow all finite values. Finite meaning countable. It goes on forever and a day. Well, that doesn't even make sense, but people say forever and a day and stuff. It's forever. It goes out, increases without end. For example, when we say the limit of x, the limit of f as x approaches infinity, we mean the limit of f as x moves increasingly far to the right on the number. Okay, just as long as you don't think infinity is a value, it is. When we say limit of f as x approaches negative infinity, we mean as you go to the left on the number. Okay. Now, the line y equals b is a horizontal asymptote of the graph of the function f of x if either the positive or negative limit as x approaches negative infinity or positive infinity. If that limit for the function gives you the value b, we're going to call that a horizontal asymptote. Well, here's a graph. I gave the graph and the tables here, but I think you now know how to come up with those. Last year I did this because Staples was sold out. That's why I told you guys in June last year to get these things, stuff like this ahead of time. Anyways, half the class still didn't have calculators, so I have it drawn up. You know how to enter this. Now, use a graph and tables to find the limit as x approaches infinity of the function and negative infinity for that function, and identify all horizontal asymptotes. Now, we know the vertical one is 0, by the way, right? You just look at the denominator. What does it look like here? I did a chart where I used 0, negative 50, then it grew up bigger, negative 100, negative 150. So as it approaches negative infinity, so it goes to the left without end, what does it seem that this value is? 1. Yeah, it's 1. And you can see the same for the other one, right? So just took a screenshot and put it in. Make sense? Okay. So A and B. So the answer for this is the limit of x approaching infinity for the function given on the graph or the chart is 1. So limit x approaching negative infinity, so going to the left on the graph, is also 1. Identify all horizontal asymptotes. Now do you see, because it flattens out around 1 on both directions, it only had to flatten out for once to call it an asymptote. We would say, and I don't have a ruler here, so it's not going to be perfect. But that 1, x equals, or my mistake, y equals 1 is your asymptote, right? So C, asymptote, y equals 1. You guys ever just say HA, horizontal asymptote? I don't care. On a exam for me, I'm fine with HA if you want to say that, horizontal asymptote. However, I will not promise you, and I don't think it's not internationally recognized, so when you write in the and, you'll only write one in an AP exam. Be careful with your abbreviations if they're just something that we use, like CM for centimeters is internationally recognized, right? I don't know about HA, that's all. Okay? This prepares us to answer page 76, blah, 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 2, 3, 6, 7. Anyways, and I gave the even answers there in case you need them. Now, I'm going to move on, but I'm just mentioning that that's what this is all about. Okay, thank you, young man. I don't want to misplace this test. Next page. Let's just see here. This sandwich theorem, remember? You got a top function and a bottom function and they meet. The middle function will be sandwiched by that value. Okay. So what we're saying, hey, this is like that one we were talking about, I think it was number 27 on our questions from yesterday. Except it was sine of x over x, right? As you go off into infinity, it just gets closer and closer to 0. And if you take a look at these values, 100, 300, 500, 700, do you notice that these, what does it mean on your calculator, by the way, when it says 8.2 E4, E minus 4? 10 to the minus 4, so 0.00, yeah, very close to 0, right? Okay. So what we said yesterday for the sine of x over x, as you go off into infinity, is that it approaches 0. Same with this, right? The cosine, no different, and it should be, it's the same argument. Now, so the graph suggests that the function oscillates up and down. The x-axis is y equals 0, the horizontal asymptote, and the value of the limit is 0. We played with them. We will use this fact to evaluate limits of rational functions at infinity. Now, think about this. As long as you know this, we can play around with these things and it'll be good. Just think about this. If this is the function, 1 over x, and just think, even if you didn't know the graph, and you know the graph, horizontal asymptotes at 0. I hope you do, right? It's with my hands and I do this, you know. You guys know what I'm talking about, right? I might be backwards. So, anyways. What is, and you just think, if you didn't recognize this right off the bat, well, what's 1 divided by 100? Oh, 0.01. What's 1 divided by a million? 0.00001. And then 1 divided by a gazillion or whatever. It's really close to 0, right? As you get, x gets larger and larger, increases. This gets closer and closer to 0. So does this make sense? I'm hoping. That's what we need to know. Okay. So what do you do with these rational functions when you got these limits of infinity? Well, you divide the numerator and denominator by the greatest degree of x that appears in, not the whole expression, but in the denominator. Then you got to stop and think. So the first example here. Numerator and denominator have the same degree. What do? Divide the numerator and denominator by the greatest degree of x that appears in the denominator. Well, it's the same degree whether I look at the top or bottom, but we're still going to think about this. A squared. So that's the greatest degree, right? So I'm going to just take 1 over a squared. Isn't 1 over a squared the same as dividing by a squared? Okay. So can I just do this? No. That changes the expression. I have to take top and bottom. Now I can do this because you're multiplying by 1 essentially, right? Same thing or the same thing. I'm not officially changing the expression. And then I drag that through here. So this is like the limit. We're approaching negative infinity. As I do this, as I distribute the division, what does the first term become? I'm going a squared divided by a squared, so 1. You guys follow what I'm doing here first? I'm distributing. 1 over a squared multiplied there and there. Okay. So that's going to be 1 plus 1 over a squared. On the denominator, 2a squared divided by a squared is just 2. 3a divided by a squared is 3 over a. minus 1 times that expression, so 1 over a squared. I'm going to stop here. Is there a question? I'm not stopping because I'm done. I'm stopping just to see. So, to review. How did I choose this? To do the top and bottom? Greatest degree in the denominator. And you just toss it through and you distribute it. And that's how you came up with this expression. Okay? Now, I said then stop and think about it. Because as a, and remember, this is not a number, so it's, you got to think about this. It's philosophical. So the limit is, I'm going to do the limit right now. Negative infinity. So as I get negative 1 million in there, or negative 2 million, or it's so and so on, negative billion. Does that affect a constant? No. It's still going to be 1. What is that going to turn into? Well, negative 1 over negative 1 million squared. I like to say 1 million just because it's a number we've heard of a lot and we're familiar with it. And it's pretty large. Or it's pretty negative in this case, negative. Negative 1 million squared on the denominator is going to make this really close to 0, ain't it? So, plus 0. Never, ever, it is incorrect to write something like this. Why? Because infinity is not a number. You can't plug it in. This is why I'm saying you got to think about it. Don't do that, right? Okay. It turns into 0. You could. We've talked about the argument. 2 is a constant. Plus, what's 3 divided by a really large or really big negative number? 0. 1 divided by a really negative number squared? Still 0. Even more 0. Now, it's really what this turns into. And did you guys remember this at all? It's often just said in pre-calc 30 or something. When you have a rational expression, the horizontal asymptote, if the degrees match, did you guys have a rule for coming up with the asymptote? Sometimes some people do, some people don't. It's just thrown in sometimes. Okay. What do you notice about the original expression? If the degrees match, it's 1a squared, that's 2a squared. It's always because you're going to divide out that 1 over a squared. You're going to multiply through that. It turns out to be the lead terms, the ratio of the lead terms. Okay? Because this is equal to 1/2. Okay. So I'm going to put a little conclusion here. The limit is the ratio of the lead terms equals the ratio of the lead. Only when the degree is the same numerator. So what happens when the denominator has the greatest degree? Well, we multiply through, just like the same choice. So I'm going to do it just like the other one. 1 over b cubed. 1 over b cubed. Well, you might see that, yeah. It'll probably be, you could quickly see, yes. But let's see here, because sometimes you get on a test, you'll second guess yourself. So work it out from first principles. And if you could see this, yes. You could jump right to the answer, just like the other one. When I paused it, I said you could jump to the shortcut. Same here. So this is equal to the limit of b approaching, now I've got positive infinity. That'll be 3 over b, 1 minus 4 over b squared. And like you said, you can see right away, it's going to be 0. So if you can see that, and then you can just, you don't have to show the word. In this case, when the denominator has the greater degree, the limit will equal 0. And you can jump straight to that. Just like the other one, you can jump straight to the ratio of the leading terms. So there's a conclusion there. Number 0. With the greatest degree on the denominator, yes. And I'm fine as long as it's that kind of a rational expression. So the first two, you can just do shortcuts for if you see them. But like I say, there's a failsafe. If you forget, you can work them up from first principles and it's not much work anyways, right? The numerator has the greatest degree. We're still going to use the same method, and you'll see in this one, there's no shortcut. So approaching positive infinity, x to the 1, x, 1 over x, 1 over x, right? We've got to use that. Because we choose from the denominator always. This is the one where people are tempted to do it wrong. So, what do you know, Joe? I know this turns into x plus 5, 1 minus 5x. 5 over x, right? Now I gotta stop and think about this. This is, you gotta work this one.
So this is like infinity?
Well, this is where you're thinking this through, yeah. This would be, like if we were choosing to think about this with a million. It'd be a million plus 5, so it's really a large number, right? A million. 1 minus 0, right? So million over, and then it's not just a million, it's a billion. You can increase it and increase it without end. It's going to go on to positive. It'll increase, we'll put down positive infinity to have that idea that it's increasing without end, right? And if you graphed it, you know, it might, this is increasing without end, like that kind of an idea, right? I don't know that particular one, I didn't put any thought. Actually, that's going to look linear, actually, now that I see them, if you did that one. Okay. So this one would actually look wrong like that. Anyway. But be careful, don't just assume positive infinity. This is why I'm saying you've got to work these out. I'll just do a couple others here. What if my next example, like this, limit of x approaching infinity, so it's approaching positive infinity. Let's just change this around a bit. If I had 5x minus x squared. So swap it and change the sign. X minus 5 again. So a variation of the first problem. Now I think you could tell it's still 1 over x that we've got to multiply through by, right? When I do that, let's see what we get. Makes you feel better, by the way. The 1 over x here. 1 over x.
Positive.
Figure positive infinity?
Yeah.
Okay, well let's take, you're a sharp cookie. Let's see. 5 minus x squared over x. So that's 1 minus 5 over x. Oh, you got, now you're just hedging all bets. You're giving me 3 answers. Something's bound to be right. Ha! Your 2 answers were wrong this time. You said,
X over x equals
let's take a look at this. You're just shooting in the dark now. Anyway, let's just think this through with a million. Like I say, a million's usually a good choice. 5 minus a million is negative something. Negative close to a million. 1 minus 0. So it's going to be negative infinity, because if you chose a billion and trillion and so on, it'll still get larger and larger. So negative infinity in this case. I wonder if that means that. I will see if it, yep, it did. Okay. You see why you gotta be careful? Stop and think. Like, think about it, because just because it's approaching positive infinity, that means this one's going down as you go to the right. Let's do one more here. X approaching positive infinity again. We'll keep x squared plus 5x again on the numerator. This time I'll change around the denominator. 5 minus x. Do the same thing, because I'm just doing variations of the same function. When I do that, once again, choosing from the denominator, we get 1 plus 5. 1x, sorry, so x. Don't forget the limit notation until you've evaluated, by the way. Naughty, naughty, I'll give you 2.5 out of 3 if you drop it too early, okay? So anywhere I write it down, make sure you write it down. If you're wondering why I did, it's maybe because I made a mistake. Ask me. Anyways, x plus 5. 5 over x minus 1. I think you see where this one's headed. Negative infinity when you think about this one because of the denominator, right? So, slow your thinking down here and don't miss, because it's a 50-50 guess sometimes, you know, positive, negative infinity, but make sure you know. Why guess when you can just figure it out? Now, I'm going to leave something for tomorrow. We'll do the functions with radicals and stuff tomorrow. So, already at the start here, I said you could try these 2, 3, 6, and 7. I'll see if that's too many. I'm going to just pause though.